Hey guys, welcome back to Pandas Data Diaries. Today I want to show you how you can find out whether a matrix is invertible. So this is a follow-up video of my last video above, see here. And of course there are some standard methods, built-in methods in SymPy to find out, but I want to show you the manual steps, how you can find out whether a matrix is invertible using SymPy. So let's dive right in. First of all, we have these three methods here, the determinant method, the rank method, and the row echelon form method. Let's first have a look at the sample matrices that we will check out in the sections below. So first of all, I'm here loading SymPy and some configuration libraries so that I can print out the matrices. I'm defining the sample matrices over here, and I'm defining a function that will display the matrices in each of the sections below. So printing this out, so we have invertible square matrix A, non-invertible square matrix B, and we also have a non-square matrix C. And we will see in the sections below what that actually means. So let's start with the determinant method over here. And here I am defining a method which takes the matrix as an input. And I'm saying if matrix shape 0 doesn't equal matrix shape 1, then return it's not applicable. What does it mean? Here, the shape 0 and shape 1 mean the rows and the columns of the matrix. So this means that the determinant method is only applicable if the rows and the columns have the same number. And actually, this is not only the case for the determinant method, but for all other methods as well, because only square matrices actually have an inverse. So we are figuring this out with this case here. And then saying, get the determinant of the matrix, so matrix.determinant. This is the standard method in SymPy. And return, it is invertible if the determinant is not 0. If it is, so else, it would be not invertible. And we can apply this to all of the sample matrices. I will do this over here. So let's print them out again. We see the matrices over here and the results. So the determinant method tells us that the first one is invertible. This one over here. The second one is not invertible, as we already defined, and the last one is a non-square matrix, so the method is not applicable. Okay, second method would be the rank method. Also over here, I'm defining the rank method, which takes the matrix as an input, and saying the same, if it is not a square matrix, which is this block over here, then do not apply the method, it's not applicable. If it is, then get the rank of the matrix and return it is invertible if the rank equals the shape. So that means if it's a full rank square matrix, else it's not invertible. So if we do have a full rank square matrix, it is invertible. And we're also printing it out over here. So again, the same matrices, rank method. So we do get invertible in the first case for this one, non-invertible for this case, and not applicable for the non-square matrix over here, as expected. The last method that I want to show you is the row echelon form method. Over here, we are defining the function, which again takes the matrix as an input and is not applicable for non-square matrices, as we already know. So we go through the process of augmenting the matrix over here. So if you don't know what's going on here, check out my last video where I went through this process. So we're first augmenting the initial matrix by attaching the identity matrix, and then we're getting to the reduced row echelon form. So there's a shortcut to do that. This is this command over here. And so basically what we want to figure out is if we can extract the identity matrix from on the left hand side from the augmented matrix after going through all of this process. So this is what is happening over here. Else it is not invertible. And this might seem a little abstract, so let me print it out what it does and it will get clearer. So over here we do have the initial matrices, and then we're going through this process. So the row echelon form method results. We do have the augmented matrix first. So we're attaching the identity matrix over here, and then we're going to the reduced row echelon form. So this is the result. And as you see, if it works, if it is invertible, we should have the identity matrix on the left-hand side here. And here we will have the result. So this would be the A inverse over here. So if you get the inverted matrix on the left-hand side, it means it is invertible. But if this doesn't happen, as in the second case, we go through the same steps. So attach the identity first, and then we go to the reduced row echelon form, but we realize that over here we do not see the identity matrix on the left-hand side. So this, if it's not here, that is a sign, or that means that it's not invertible. If it's invertible, we always have the identity on the left-hand side. So this is also what it says. And in the last example, we defined that it is not applicable in the first place if it's not provided in the correct format. So we went over 3 different methods to find out manually if the matrix has an inverse or not. Of course, as I mentioned in the beginning, you can also use SymPy standard feature to get to the same results. So let me show you over here what that means. If we use the standard method, which is just .inv, we see for the first matrix that was invertible that we also get the inverse over here. But for the second case, for the non-invertible matrix, we will see that we get an error. So here the standard function .inv returns a non-invertible matrix error. And this is what we expect, because it's a non-invertible matrix which doesn't have a determinant, or using the other methods, you get the same results. And the standard function also returns this error. And in the last case, we are using the non-square matrix as an input to .inv. And let's see what we're getting. We're getting a non-square matrix error, as expected. So we can only use this approach with square matrices. That's all I want to show you for today. I hope this was useful, and see you soon again back on my channel.